We're going to start talking about time and space stepping schemes. So this is basically solution techniques for partial differential equations. And what we really want to focus in on now is how do you march solutions forward in time. So this is going to be called the method of lines, in which we're going to construct progressively the solution at one time point, which is we're going to call it a line, advance the solution delta t into the future, and that's going to be the line of delta t in the future, advance it again to the future delta t, so now we're 2 delta t into the future, and so forth and so on. There's a lot of considerations in how you might develop time stepping schemes. In fact, we're going to show quite a diversity of ways you can develop time stepping schemes. And one of the big primary considerations, or there's two naturally that we want to consider, one is accuracy and the other is stability. You can't just simply make an iteration scheme and expect that it will actually be stable. In fact, many of the numerical stepping schemes we're going to consider are unstable, and so part of our job is to think about how do we construct stable schemes to march forward into the future. So I'm going to just remind you that since Newton and calculus, so Newton laid down this foundation and Leibniz about how we take differentials, and then within the context of this calculus, two basic quantities of calculus, which is differentiation and integration, we were able to construct the laws of physics. Up to that point, what we had was geometry and algebra. But now that we have calculus, we can start talking about, we have a whole new language for representing physics. And in fact, all of physics engineering really is relationships among derivatives, both time and space. And that's how we express physics in these days. So let's give you an example. Here's Maxwell's equations for electrodynamics. So here's electric field E and the magnetic inductance B, and this is related to the electric magnetic field H. And so here are these quantities and how they evolve in time and in space. You can see the time derivatives are here, and the space derivatives are basically in these curls and dots here, divergences and curls. And so when we think about electromagnetism, it is a relationship among space-time dictated by these derivative relationships. That's one way to think about it. And Schrödinger equation in the same way. This is the underpinnings of quantum mechanics and how we evolve probability distributions in time and space for the location of an electron, for instance. Navier-Stokes, same thing. How do we start talking about fluid packets, conservation of mass and momentum, and then what we have here is, again, time derivative along with the quantities of interest that we want to look at. So again, all of this is relationships among derivatives. And what we're going to focus in now is how do we evolve things forward in time. Okay? In the last set of lectures, we talked about all the things that you have to start thinking about once you do discretization. And so now let's think about the things we're going to have to really consider when we're going to march forward in time. So the place that we're going to start with some really basic time stepping schemes, build from there towards how you can construct time stepping schemes and what their stability properties are. Those are the important things to be considering when you choose a scheme. Easiest place to start is the heat equation. It's got one time derivative, two space derivatives, so seems very easy to handle, but we'll see that you can't just make up any scheme to make this thing march forward in time stably. So we're going to talk about how you might construct schemes and what will happen. So let's do the first basic scheme we might look at is something like this, where what we're going to do is take the second derivative and use a center difference formula, second order center difference formula, which says if you take two derivatives, the derivative formula says you have minus 2 of the current point you're at, one of the point in front, one of the point behind. Okay, so x plus delta x, x minus delta x, and this is how you compute a second derivative. Immediately, what we've done here is a discretization, where we're going to look at this along the x direction with a grid size of delta x. We've already talked about discretization and all the things that discretization implies, but now we're going to use this for this time stepping scheme. Okay, once you've got this, we're going to organize the data. So let's go back to our discretization scheme here. Organization of the data is we're going to make a vector u, and u will contain all the points from going from negative L plus delta x, negative L plus 2 delta x, all the way to U of L, which is the endpoint here, which is the input point. We're going to have periodic boundary conditions on this to start with. So first is the organization of the data, and the data matrix here, U, gives you all the discrete points in the spatial domain of U. Okay? So this is going to be a vector. Everything's going to be discretized into vectors and matrices. So once we have this vector formulation of the heat equation, in other words, we've discretized this, now we start to figure out how do we represent this in terms of differential equations. So here's the equation again, and now the claim is that once you've done this, this second order derivative just turns out to be a differentiation matrix A. And so in fact, remember that we take the difference divided by delta x squared, so there's the delta x squared. Here is the diffusion constant. The matrix A itself takes this structure here. It's negative 2 along the diagonal. So you can see that here, that if you walk down this diagonal, right, you're going to have negative 2's, and then 1 on the off diagonals on either side. And that's just due to the structure of this formula here. Negative 2, 1, and 1. So that's what you have in terms of this partial differential equation turning into a differential equation of size n. Okay? And the size n is just simply based upon how you discretize the size of your domain. Now, it turns out picking the delta x that you might have here has an enormous impact on the time step you're going to have to take here when you march forward in time. You might be tempted to just say, oh, I could just use an ODE solver here. In fact, you could. But we're going to talk a little bit more in more detail that you have to be very careful what you do at this next step in terms of picking out your time step after you've discretized. So let's first of all build a little code for how we might in fact solve this. So first you're going to define the domain, so some t-span on which I'm going to solve this from 0 to, I'm going to solve this from 0 to 2 in steps of 0.2, so this is where I'm going to write out the data. Okay, I'm going to break it up into 100 points. I'm going to pick the diffusion constant to be 1 and domain length to be 20. So this is what I've got here. And so first I define my domain then. It's going to be a linear space, goes from negative L over 2 to L over 2 in n plus 1 points. Remember, I'm going to do periodic boundary conditions, so the last point is the same as the first, and that's what I've done here is I've just taken the first n points. And my dx is just the difference between the 2 points themselves. So I've set up my domain and my discretization. And again, this choice here of, of picking the number of points I have, which is 100, determines the delta x, right? So once I've decided a domain size, and if I cut it into 100 points, that determines the delta x. Turns out that delta x will have a big impact on how we choose to time step forward and how big a delta t's we can take marching forward to get stable solutions. And that's really what we're concentrating on these next set of lectures is how do you set up stable schemes for yourself so that you can get accurate solutions that are true and faithful solutions to the system and not blow up or go unstable. So let's now build that matrix A. The matrix has negative 2 on the diagonals, 1 on the off diagonals. Again, we're going to use the SB diags, which is the sparse diagonal matrix structure. So I'm going to make a vector of 1s, and then I'm going to tell it what I want to do is put 1s, negative 2, 1, and where I'm going to put them is on the off diagonal, the diagonal, and the off diagonal. So this is where what I'm going to put down, where I'm going to put it down, and here is the simple matrix that I'm going to use for this, and it's an n by n. So once I have that, I've got my basic matrix structure. I put in the boundary conditions here due to periodic boundaries, so 1 on each corner of that matrix. And now what I have is my differentiation matrix. And this takes 2 derivatives in space with periodic boundary conditions. So if I take a vector and multiply it by this matrix, it takes 2 derivatives, subject to periodic boundary conditions. So I've got all the ingredients I need to now solve this system of differential equations, which was originally the PDE, is now ODE set. And so I can just basically take this, for instance, if you are going to use an ODE solver, all you have to do is define the right-hand side, which is k over dx squared, a times u, and you just call this ODE solver where you put in, you call the right-hand side, give it an initial condition, give it a t-span, the arguments you want to send in. So this, in other words, this is sort of framing it in the way we've already talked about ODEs, and now this is framing it back in terms of simply a classic ODE way of thinking about it, if you want to step this forward. So, but what's disguised here is, what about the stability properties? How do we start thinking about, if I pick a dx, what does that mean for my dt? Because there's big implications. They are not separate. They are intimately entwined in terms of building stable stepping schemes. By the way, this whole flow that we've done here follows through directly to if you go to higher dimensions. So for instance, I want to just show you what happens in 2D. So here's the 2D heat equation. And the 2D heat equations, you have two derivatives in x, two derivatives in y. We've already seen how to discretize this matrix in our previous lectures to make a matrix A that, when you organize the data, it takes two derivatives in x and two derivatives in y. But let's go and walk through a little bit here how it would look like. Essentially, when you do this, you're going to discretize again into this matrix into this ODE solve right here, which is U is a vector of all my points. A is the matrix that takes two derivatives in x and two derivatives in y. I have the k and delta squared here, and this is how I've arranged my data. Now, we've already shown how to do this. So again, it goes back to organizational principles. It is your job to organize all this data in a meaningful way, and this is how we're going to organize the data into a vector. So in other words, even though it's two-dimensional, or you solve three-dimensional problems, you're always going to organize it into a vector, and then derivatives are simply going to be matrix multiplies. First derivative, second derivative, two derivatives in x and y. You're going to construct these matrices that act on the vector to produce the derivatives you want. Okay? So this is the organization of the data. Let's talk about how we might do this in practice for coding. So you might define an x domain, a y domain, in this case each 20. You decide the discretization in each domain. Here it is 100 in each domain. And what we know is we're going to have the total size of this matrix is going to be nx times ny. So if I chop this up into 100 points in x, 100 points in y, then the number of ODEs I'm solving for is 100 squared, right? So 100 points in one direction or another, I've got myself a 10,000 by 10,000 system of equations to solve with my ODE solver. So you can see, as I make it more and more refined in space, as I discretize finer and finer, I get a larger and larger system of differential equations that goes like the square of the number of points. So keep that in mind, because that's your computational cost you have to deal with now. Okay, so that's important when you think about it, because partly what you'd like to do is solve the solution, get the solution as quickly as possible, as accurately as possible, and so making good choices here, make good choices, is really important. Okay, so that's how we think about it, and then I can just decide on sort of how to define the domains. Here's the x domain, so in other words, I chop it up into x to 101 points, and I just take the first 100. Remember, I'm assuming periodic boundary conditions. Same for the y, and then I mesh grid it to get a two-dimensional representation, and then I pick an initial condition. I reshape this. So that's the important thing. At the end, I'm going to reshape all my two-dimensional data into 1D, and I already would have the matrix A that we built from the last set of lectures, which takes two derivatives in x, two derivatives in y with periodic boundary conditions. And so once I have that, when I call the ODE solver, it's exactly like the 1D case, except for now the matrix A is much bigger, the initial condition U is much bigger, because now I'm in two dimensions. So instead of 100 points coming in when I discretize, I have now 10,000 ODEs I'm solving simultaneously. So basically what we're philosophically doing is, the reason this is called the method of lines is because what we start with is at time 0, the solution along this line here, which is the t equals 0 line. Okay? And what we do is we update the solution. We're using our neighbors because it's a second derivative, and the second finite difference scheme we use for the second derivative relies on neighbors to update the future point, and so that's what this means here. So as I update to the next line of solutions, which is T1, I'm using at each point the previous history of neighbors, of two neighbors plus the point itself. To get T1, I advance it again to the next line, and so forth. So I march the solution forward in time along these different timelines. Okay? So time is discretized, space is discretized. We've spent a lot of time already talking about spatial discretization and looking at how you would take care of and handle the commitment to discretizing space, and now we're going to focus in on this process of marching forward in time. So that's the basic structure here, and the concept that where we really want to spend our effort is thinking about a stability of schemes. When we march forward in time, we want to make sure we have a faithful representation of the solution, and of course we want as accurate a solution as possible as well. So we're going to cover some of the key issues we have to think about in these time-space stepping schemes here in what follows.